Welcome to Ask and Learn.
Alright guys, we're going to be doing problem number 80 of chapter 5 in Chemistry, the Central Science. So methanol is used as a fuel in race cars. So in part A, they want us to write a balanced equation for the combustion of liquid methanol in air. Alright, so I'm just going to open a new tab to give it some more space. Okay, so liquid methanol is going to react with oxygen, produce CO2, and it's going to produce water, but in its gaseous form, not its liquid form. So we have one carbon. Now we got to balance this. One carbon here, one carbon here. Now we have two hydrogens here, four here. So we're going to add two here. Then we have two oxygens here, so four on this side. Then we have two on this side, so we have to double this. So now we've balanced this equation. Now we're going to calculate the enthalpy for the standard enthalpy change for the reaction. So remember, it has this law, delta H of reaction equals delta H of the product. Delta H of reaction is delta H of products minus delta H of reactants. I just put A here. Now we're going to look at B. B, we have two oxygens. So we have two waters. So 2 times minus 238.6 minus 393.5. That's right, the CO2. Then subtract the reactants, which is minus, that's the wrong one. That is for methanol. Oh, we need to use 1 for steam. So 241.82, then minus 238.6. So that makes our delta H of the reaction 2 times negative 241.82 minus 393.5 minus negative 238.6. So that delta H for reaction is minus 639 kilojoules. Now they want us to calculate the heat produced per liter of methanol. Thus, so for C, remember we have we're using 1 liter of methanol. So remember, 1 liter is equal to 1,000 milliliters. Density of methanol is 0.791. So that means we have 791 grams of methanol in a liter. Now we're going to convert this to moles. So we have 32 grams per mole. So 24.7 moles of methanol. Now we're going to multiply this times this amount of heat here. In fact, this should be kilojoules per mole. Mole, not just kilojoules. Joules, just to be clearer. .7 times 639 moles, so 24.7 times 639. That's going to be equal to negative 15,783 kilojoules. So that means 15,783 kilojoules. That's how much energy is released. That's is per combustion from a combustion of a liter of methanol. Now, we're going to do part D over here. So they want us to calculate the mass of CO2 produced per kilojoule of heat emitted. So we have, in our balance equation, we have 1 mole of methanol, 1 mole of CO2. So number of moles of ethanol is equal to number of moles of CO2 in this reaction, which is equal to 24.7 moles. That's how many moles of CO2 we have in this equation. Now we have to convert that to to mass. So M of CO2 is going to be 44 grams per mole. Times 44. 24.7 times 44 is 1,806.8 grams. And we have to divide that by the amount of heat that's emitted. So we're going to divide this by 1,086.8 over 15,783. 3 kilojoules. And so that's going to produce 0.069 grams per kilojoules. So that means that 0.069 grams are produced for every kilojoule of energy produced.